So I'm going to talk to you a minute first. I'm using some notes that I'd already created for a finite math class, which is the prereq college for business calculus. So supply and demand can be given as functions in terms of price. And it's a quantity price relationship. So sometimes when you increase the price, more people will buy it because there's this kind of perceived value situation. But generally speaking, that's not the case. So generally, if you increase the price, fewer people would buy it. So if I had the same product, let's say that I was doing a fundraiser and I was selling Hershey bars. So they're usually kind of large Hershey bars, and people, well, at any rate, in the past would sell them for $1. So whatever they sell them for now, I don't know. But suppose I was selling them at $1, then I could probably really sell quite a few chocolate bars because I've seen those go and I've done it myself. And so you pay for the chocolate bar, no problem. If you raise it to $1.50, some people are now not going to buy it because now it feels like it's not a good value more than the dollar. If you were to sell it for 50 cents, you could sell it all day because now you're cheaper than Walmart, right? So generally speaking, as price goes up, the number you can sell goes down. On the other hand, if I'm the person selling them, then my willingness to supply the chocolate bars increases as I get more money each for them. If I'm selling them for 50 cents, I'm not making much, if any, profit, so I'm not very motivated to come up with the chocolate bars. If I'm selling them for $1 each, I'm making sort of a small amount of profit per. So I'm kind of motivated to sell the chocolate bars, but at $1.50, I'd love to sell more chocolate bars. So the demand is how many people will purchase it at a given price, and then the supply is how many I'm willing to create at a specific price of sale for me. So if I knew, for example, so let's say I was trying to come up with a demand function. So there are two different things going on. For the market equilibrium is where supply equals demand. So we'll talk about that in a minute. But I want to note that there's a slightly different situation that you guys are going to deal with, which is maximizing profit. Because market equilibrium doesn't necessarily maximize profit. So when you're looking at it, you're going to have at least two values, hopefully more, that you'll find out. Let's say it was the Hershey bar. Then if you did a survey and said, okay, would you buy the Hershey bar for 50 cents? Yes or no? Would you buy the Hershey bar for 75 cents? Yes or no? Would you buy it for $1? Yes or no? And so forth. So you'll get these kind of points that say, well, at 50 cents, X number of people will buy it, or X percentage of people. So if it's, say the percentage here is 0.8, and then you have 0.75, so 0.75, 0.7. At $1, 0.43. At $1.25, 0.37. Okay, so let's say it's this. Then you can translate this into, at 50 cents, it's however many people, so 0.8 times the about 300 that we have, so about 240, 0.75, how many people, so now 210, and so forth like that. Then you'll be able to put these in as X, Y points. And because we're just about to be studying correlation, you'll get a line of best fit, which you'll then use as your demand function. So you'll have, remember that this is P and this is Q. Okay, so you're going to get a Q equals some, and we'll approximate it linearly unless you are motivated to get an advanced or a distinguished, I guess, and then you might try other lines of fit. So this one's going to look something like, let's see, here's 0.5, $1, $1.50. So 0.5, if that's 1 to 0.8, 0.75 to 0.7. At 1, we go quite a bit down. At 1.25, we don't go much down. So this is really sort of like that, but you'd get a line of best fit that would be, I'm always bad at drawing lines on this tablet, something like this. Okay, so you'll get this line from RStudio. You'll do a linear regression and it'll give you that line. And so you'll have Q equals AX plus B, whatever this is, okay? Once you have that, remember this is demand. For maximizing profit, what you really need is demand. And so we'll get into that a little later, but I just want to let you know that this is something slightly different. So market equilibrium, you would have a supply function that's written in terms of P and Q. You'd have a demand function that's written in terms of P and Q, and you would set them equal. So one of these days I'm going to learn how to do this. Okay, so market equilibrium, Q or P for supply equals Q for demand. Okay, so now let me go over to these notes. There's another thing called a break-even point. Generally, when you start making a product, as you guys already know, you have to kind of sink some money into it before you're ready to sell anything. Even if you have investors, they're putting out money, but it's very unlikely that you can start selling a service or a good prior to having spent something for advertising, for a space, for even if you're doing a car wash, you have to buy the soap, right? So when you break even is when you've sold enough pieces of your goods or services to equal the amount of money you've spent at that time. So at that moment, you have zero money, but you no longer have negative money. So it's a good thing. If you ever hit a break-even point, then you're on the right track. Okay, so we usually use capital C for cost, capital R for revenue, capital P for profit, so then it looks like probability, which isn't great. But if the thing in the parentheses is not a capital A, B, C, D, E, that indicates an event or a word, then it's probably profit instead. Also, of course, these are different topics. One's economics and one's probability. So let me grab this, clear this. Okay, so if we want to find the break-even point, then we just set break-even C equals R. That's also when your profit is zero. So profit, just always, you take whatever money you brought in and you subtract the money that went out, right? So it's revenue minus your cost. So if revenue minus cost equals zero, then adding cost on both sides, revenue equals cost. So this is the same thing as profit equals zero. Okay, so we set these equal. And we see a quadratic, and then we remember from algebra that we need to set this equal to 0. So x squared plus 40x minus 130x plus 2,000 equals 0. So I've rewritten it in the normal form you're used to looking at so that we can think about factoring. You can also use the quadratic formula. You could also use your calculator to solve for zeros. This one's not so bad, so I'm just going to go ahead and factor it. Oh wait, that's not quite right, is it? Minus 40 minus 50. Oh yeah, it is. Okay, so x is either 40 or 50. So we have two places where we've broken even. And what we have is profit is revenue minus cost, so profit looks like this. So basically we have a point where we broke even, but then as we keep increasing, at some point we can't sell it for enough, so we start losing money. So here our negative profit was because we'd sunk the money into it and hadn't started selling enough yet. Here we started selling enough, and so we started having a profit, but here it was too many. So we created so many that we had to sell them for less than we paid to make them. So now we're back in the negative, and really, where you really want to be is right there. Okay, I'm not going to graph the profit function, although we could. But the first question, is the vertex a minimum or a maximum? That negative value in front of the x squared means that we have an inverted parabola. So the vertex is going to be a max. It's going to be up top. And then we want to know, actually you don't need to calculate that. So what you would do here to maximize profit is find the vertex. That's part of why it might be easier, although you're probably so good with your calculators that it wouldn't be. But if you model your demand function with a line, then you'll end up with probably your costs will also be linear. You'll probably have a set fixed cost that you have to spend no matter what, and then a cost per item, so that your cost function will actually be linear. So if you take two linears together and then x number of products, then you end up with a quadratic. And then when you do that, you just have to find the vertex, and the vertex gives you the maximum profit. Okay, so here's another break-even point. So we have a fixed cost of $300. We have a variable cost per unit of this amount, and we're going to want the break-even points, and we're going to want the maximum revenue. So let me grab this. I know with the video you don't need 85 examples, so I'm not going to necessarily find the break-even point. You can find that, revenue equals cost, but I'm going to actually just calculate the profit function. Not calculate, that's not the right word. Create, write, interpret. Okay, so we have a fixed cost of $300. So cost in terms of x, the x part doesn't matter for the 300. I've just got a 300 and it's just gone, spent. A variable cost per unit of this. So this times the number of units. This is per unit, so this times the number of units. X is the number of units. This is the selling price per unit, so that gives me revenue. And again, it's per unit, so whatever this is per unit. So if I just kind of, work these out and combine like terms, then I'll have these profit being revenue minus cost. See, it looks like a parentheses, okay? Is 1500x minus 1/4 x squared, so I just distributed the x, minus 300 plus 3/4 x squared plus 1460x equals, so I have minus 1/4 x squared minus 3/4 x squared is minus x squared. 1500x minus 1460x minus 300. Okay, so this is my profit function. So for the break-even point, I set this equal to 0. And I really want to factor it because it's very easy, but I won't because I said I wouldn't. So you would set this equal to 0 and solve for it, and that would be your break-even points. And if you wanted to maximize profit, you would just do the vertex of this function. And you don't have to put it in vertex form for that. I want to note something to you. This is something that you should know. And basically, because everything's symmetric on a quadratic around the vertex, you should realize that when I add and subtract something to get the zeros, then the thing I started with is the middle of it. So negative b over 2a plus some stuff, or negative b over 2a minus that same stuff, those are the zeros. So here's one, here's one. So the vertex ought to be in the middle. So the vertex is at the negative b over 2a part, because that's what had stuff added and subtracted from it to get to the zeros. So you can always just do negative b over 2a for the x value. And then you could solve anything else you wanted. You could solve the profit, the cost, the revenue, whatever, but that's where you're going to maximize the profit. So we just found the number of units that generate the profit is 20. The maximum profit, you just plug it in. And then the price that will generate it is where you put x in right there. So it's 3/4 times 20 plus 1460. So 15 plus 1460. So 1475 would be the price. So once you find the variable, you can just go plug it back into anything to find what they're supposed to be. Okay, so now I'm going to do 2 examples of how to find market equilibrium. And again, that's just where supply equals demand. So that may not maximize your profit, but what it does is you don't have people who desperately need an object, and you don't need a bunch of spare objects that nobody will buy. I'm doing a lot of things that I don't mean to do. Okay, there we go. So we just set q squared plus 8q plus 16 equal to 216 minus 2q. If I had been given this in some other way besides p equals, I'd have more work to do, but p equals means I can just set these two equal. So I'm going to get 0 on one side because of that squared right there. So plus 8q plus 2q plus 16 minus 216. I factor it or I use the quadratic formula. And so q equals either negative 20 or 10. And this is where we consider the reality of the situation. The number of products that I make cannot be negative. So it must be that the result I'm after is the 10. Okay, sorry, I went to pause the recording to save it so that it doesn't delete it like it has in the past. Okay, so we take that the quantity equals 10. That means the price is 216 minus 2 times 10 is 196. I could have also plugged it into there. We had set these equal, so that quantity will give them both the same. I just didn't want to deal with this quadratic. I'd rather just deal with this line, so I chose the line. Okay, so this one just said supply, demand, and now they're giving us this. The supply function for commodity is given by, and the supply function is given by, okay? These are not P equals, nor are they Q equals. And frankly, if we go in and try to solve for q, we're going to end up with fractions that nobody that I've ever known is super keen on. So let's try to be as kind of clever with it as we can. But note that you could just solve for q on one of them and plug it into the other one. It is something you could do. What I'm going to do, because I see p squared in both cases, and I don't see a regular p, it's just a p squared, I'm going to solve for p squared in one and plug it in for p squared in the other, just to make my life a little bit simpler. It's not different, okay? When I do that, it's possible I'm introducing additional solutions, but I'll figure out which ones make sense if that's the case. So p squared, oh, well, that's a squared. So p squared equals 1600 minus 4q. So that's from the first one. So I'm going to go to this one and say 300 minus, and I'm going to substitute in. So it's sort of like when you're doing solutions of linear systems, where you'll take one from one and substitute in from the other. And when you do that, you're actually setting the thing saying both are true. So before, when I set p equal to p, I was saying both of these statements are true. So now I'm just saying both of these statements are true in a slightly different way. If they're both true, then I can make the substitution. As long as you're taking from one and plugging into the other, you're still doing the job. Okay, so now I have 300 minus 1600, 4q plus 2q. This isn't going to divide very well. So 6q equals 1300. Okay, so the quantity is going to be 217. Hope I didn't delete a solution by substituting for the p squared. I'm going to go back and do it over just to make sure. But so right now I get 217 because quantity has to be a whole number. And then that means that p squared equals 1600 minus 4 times 217. So p equals the square root of 732. I think I must have screwed this up somehow because I think this used to work, but maybe it didn't. Okay, so suppose that you were going to do it in the careful way and substitute for q. Oh, one of these should be a demand function. Supply, supply. I needed to rewrite these notes, I think. Okay, but I'm going to try. So I could say for q, okay, so over here I have 300 minus p squared plus 2 times this is this over 2. So I have minus p squared over 2, 800 plus 300, No, it's the same. Okay, so I just need to rewrite these notes and make it better. But anyway, we will have, well, we don't actually have to solve for market equilibrium because that's not our goal. But hopefully, if I give you some problems over this to practice this for economics, you will not have crazy weird things that people accidentally created. So there we are. Okay, so that's the end of those notes. I will get with Miss Platt at some point to find out what else she wants addressed in this mathematics-wise, and I'll get back with you.